the topic about exponential growth. Okay. Now, given a quantity, okay, given quantity, this quantity could be the population, could be, yeah, usually would mean the population. Okay, also amount of a radioactive material. Okay, and that Q, okay, is some quantity. Yeah. So the derivative of that quantity with respect to t is usually the time. Okay, is the rate of change of the quantity with respect to time t. And that rate, in some cases, we find out is proportional to the quantity. Okay. Yeah, it would be surprised. Yeah, this is a, well, it's not surprising. Yeah. If you find out the rate of change depends on proportional to the quantity. Now, sometimes it's not proportional quantity, but in some cases, proportional quantity at the very beginning. For example, if you put some bacteria in the container, right? And only a couple of them. At the very beginning, the population of bacteria will grow, the growth rate will be proportional to the amount of bacteria. Just duplicate very fast. Yeah. And later on, of course, after they occupy a whole container, then it'll be changed. It cannot grow, continue, right? It'll be slowed down, when almost occupy the whole container. Okay. So the population of the human being around the Earth, just growth according to the same formula. The growth rate of population is proportional to the population, but the Earth is limited, right? The surface of Earth is limited, so you cannot have like 1,000 billions of people on the Earth. So eventually, it will be stopped, even reverse. The population drops instead of grows. In Russia right now, even the population in Russia, I think it decreases. It's not grows. The population in the United States still grows. All right. So this is a big question. So we try to figure out what kind of you're trying to solve this equation. Okay, and we will get an exponential function. Okay, Q will be the exponential function. Okay, some constant, so y. Now, before we solve it, let's look at this. Okay, if Q equals a constant. Okay, let's say constant, some constant. Okay, k. Well, I'm using a different constant. I don't want to use this k. Okay. So this is some constant, okay, a to the t, okay. Then you differentiate, and the constant stays there, and a to the t natural log of a, right? So this will be, this is your constant, right? So this is natural log of a, and then c times a to t is going to be q. So if q is a constant times the exponential function, then q satisfies this equation. So I think if we try to solve this equation, we'll probably end up with a constant times exponential function. Okay, how do you solve it? Well, I divide both sides by q. Okay, then you get k, right? Then I integrate. Can I do that, right? Then I integrate with respect to t. Okay. Now, if I integrate, how about the left-hand side, right? So use substitution. Okay. You use substitution. You let u to be. Okay. Use substitution. Okay. Just let just q actually. Okay. Q. I don't need to introduce q is already the quantity. So this part is nothing but just the q. So this integral will be 1 over will be something like that, okay? Then we know that antiderivative 1 over q is natural log over 3 by q, and the right-hand side is k times t. Since it's indefinite integral, I have to put a constant c here, okay? So we almost get the solution. Then I put the exponential under that, right? Put an e under this. Okay, what I get here is an absolute of q. And this one is e to the c, e to the kt. Okay. Now, e to the c is always positive number, but if you remove the absolute value symbol, if you remove the absolute and you get a plus minus e to the c, e to the kt. Okay. So what is that number? Well, if you let t to be 0, then plus minus e to the c, and here k times 0, right, which is 1. So this constant, possibly positive, negative, is just the initial value of the quantity. So therefore, we get a general solution. Okay, so this is a solution to that equation dq dt equals kq. Okay, q is a function of t. So you get a solution. So if you are told that the quantity is a proportion, the rate of change of the quantity is proportional to the quantity, then it must be can be written as an exponential function multiplied by a constant. That constant is the initial quantity. All right, and then you probably don't need to repeat this whole procedure as long as you're told that the quantity satisfying this equation. We call it differential equation. Okay, then you can write down the formula right away. You don't need to waste time to repeat this whole procedure. Okay, so let's try to solve a problem. Okay, this is about world population. Okay, so according, when you do some analysis on historical data, right? So you find out in 1950, that's 2,560 million people on Earth. Okay, but in 1960, 10 years later, 3,040 million people. So clearly it's growing. And that's lots of human beings on Earth, right? So we assume, okay, the growth rate is proportional to the population. Okay, assume that. And then we find out that this probably is true. We can use our formula to predict the population, for example, in 1992 or 1991. Then you check the data. They find out the population we use in mathematics calculate is a match with the actual data. Then you say, okay, indeed, this is a correct assumption. And then we can predict the population in 2020 or even 2040. Now, if nothing serious happens, such like World War III, or like a very severe virus, not like coronavirus, some viruses much, kill 10% of people population. So that happens, then the growth rate to be changed. Okay. Proportional to the population. Okay. So that means dp dt equals k times p, and k is a constant, right? So in reality, this k is not constant. You can only say k is almost constant. Right? K could be changed from positive to negative, like the population in Russia. The population growth first has a positive growth rate, then and then it's become negative. It decreases. Okay. All right. So let's So once we see this, right, and I don't need to repeatedly to derive the formula. So we know that the form it's going to be P. Let's just put this now there. This is the initial value. Okay. So this is a yeah. This is a if you want to put a T there, and this looks like that. Okay. This is the initial value. Okay. Doesn't matter which notation you use. Okay. First of all, we have to set time. For 1950, we set the t equals 0. Okay. Yeah, that's our initial time. So that means P0 P of 0 is going to be 2,560 million. Okay. Okay. So now, what do we get? We get a partial formula. Okay. So that under our some assumption, the population grows exponentially. And then let's try this. Right? Then what do we have to do? In order to predict the population in the future, we have to determine the constant k. So we need another data, right? So 1960, t is going to be 10. So p of 10 equals 2,560 times e to the 10k, right? So we know this value is going to be right 3,040. Okay. So now you get an equation. This equation only involves k. Okay, I'm not going to use a calculator to do some estimate. Okay. So what I got here is e to the k. The 10k is going to be 3,040, 2,050, 2,560. Okay. Right. Okay, so let's, you can write down, you can put the answer here, you put a natural log on both sides, probably don't need it. You put a natural log on both sides to find the k. Okay, don't be in a hurry to use a calculator to estimate, okay? So this gives you 10k, k is going to be 10 over natural log. Okay, and you can even write it in this form. Okay, right? Good. Doesn't matter which form you use. So you get it. If you write in this form, you can you can express the pt without using e. Okay, so let's see what is pt, right? Pt again 2,560 e to the kt, right? And e to the kt is going to be e to the k times t, right? To the t. So e to the k, what do you get? If you put e under the k under that, 260, right? So this is actually e to the k is nothing but this is going to be that. So I can put 3,040, 2,560, and 1 over 10 and times t. You see? So you can even express this formula for the population without using e. Okay, so it is a exponential function, constant times exponential function. That's okay. Now, in 1993, okay, and that means t is going to be 43 after 1950, right? Okay, so in 1993, what is the population based on this formula? In 1993, if I can use any of these formulas, okay? I can use this formula, it's 2,560 times and 43 divided by 10 is 4.3. Then you can use you have to use a calculator to estimate, okay? Now, probably there's no, it depends on, if you scientific calculator user, you can estimate that. And this is going to be 5,360, pretty scary, double, right? All right, so 5,360. Then you look at the data in the history, it's almost like this number. So that means our prediction is correct, okay? So what is K? The growth rate. So K, if you go back to estimate that, it's going to be 0.017185. So it sounds like if you use a percentage, the growth rate is, it's about 1.7% growth. It's about, okay. All right, so in 1993, this is a population already. And, there was no World War III and no severe, serious violence spread out. So that is what we get. Okay, now 2020, that's the last year, right? You can look at the data on the internet. What is the world population? And based on our calculation, you have 70, and this is you can use the number already got a K. Use this formula 0.017185. Okay, to do the calculation. You can also use above formula. Use this formula. Doesn't matter, right? If you use this formula, you T when T equals 70. Okay, you can use that without using calculator. You can probably solve the problem by hand. Why by hand? Because this is just a 7 square. All right, 7 square. Okay, so 7. Just 70 divided by 10 is 7. So you just do 6 times, right? So you multiply the amount and do the division by hand. You say essentially within 1 hour, probably can finish the computation. So it's about 8,524 million people. Okay, let's use a million. Okay. I don't want to use a billion. Okay. So that's a population. Okay. And it's pretty scary, if this continuing growth, right? And there'll be not enough food to feed everybody. Okay. United States, there is no big problem. We have lots of land and exports lots of food also. So, but eventually, we will face this problem if the population of the United States grows and to like a 20 billion, that's impossible. Yeah, so that will be a bigger problem then. Okay. All right, so that's about population. This is a problem. We need a data, initial data at least, right? And another one as a population. Then you can determine the coefficient and the growth rate K. Then you can predict the population. If what you predict doesn't match with the computation, then you have to figure out what's wrong with that, right? Is there any change, between 1960 and 2020, right? This period of time, maybe something changed. It's different from the 10-year period between 1950 and 1960. Right? Otherwise, if it's a similar situation, then that should be good. With the same growth rate, then you should have the population should be 8,524 million. Okay. Right, so mathematics can be used everywhere, lots of places to do the computation. Okay, and the more area depends on mathematics. Okay. Students in engineering, usually, they must learn lots of mathematics. That's required. Yeah. Electronic engineering and mechanical engineering, they require different mathematics. Okay. electronic engineering require more like equations, how to solve equations, this kind of stuff. Electronic and mechanical engineering requires some modeling, like geometry, vector calculus, okay, multivariable calculus. Okay. But so let's take a look at this formula again. Right? E to the kt. Now k could be negative, could be positive. Okay, k is called if k is negative, if k is positive, k is called as a Gross rate. Gross rate, and the quantity decays grows exponentially. Then we said that, right? When the k is negative, well, it depends on sometimes we remove the negative sign, and this is called the decay rate, right? And it decays exponentially. Okay. Now about radioactive material, okay? The amount of radioactive material decays, right? And we find out it decays exponentially. Okay, no matter how do you try to, usually people don't try to change it. Not like a population, If the population is too high, then there'll be not enough food, for example, right? So people will volunteer to produce less babies. Okay, but the radioactive material, it's there. Usually we don't touch it, right? So that the constant will be not changed. Okay. So it's decay. So we assume, okay, right now we assume that k is negative, okay? Then we would like to know when the quantity becomes reduced to the half of the original, okay? So we want to find the t. This is called the half-life, okay, such that the quantity of the time t, capital T, is half of original quantity. Okay, and let's do it. So this is the left-hand side is going to be Q now there, e to the capital Tk, and half of Q there. You will find out the half-life is independent of initial quantity. So it's given by this formula, okay? And you can solve for t if you know k. Sometimes you are given t, sometimes you are given k. Then you can determine one of the values. But whatever you get is, you should get k times t equals natural log 1/2. Okay? Then if you want to get k, and you solve this for k. If you want to get t, you solve for t. Okay. Yeah, we needed to understand this formula. So sometimes you're not told it's half-life. You say at what time the population is reduced to the 10% to the 10% of the original quantity. It's a similar idea. Instead of 1.5, there'll be 10%, 0.1, okay, to the original quantity. Right, so let's find let's solve the problem here. Okay, we're talking about the radium 226. Okay, so the half-life, we know that the half-life T is going to be 1,590 years. Wow, that's really compared to the life of human being. It's a very long time, right? So that's why we start to worry about how about our nuclear waste. Lots of them put in the state of Nevada. and you know, like 100, 500 feet deep somewhere. But if we have too many, how do we do too much? How do we do that with this? Right. Right. So we want to find the formula here. So we assume that a sample, right, has a mass of 100 mg. Find the mass after TS. Now let's find the formula, right? So we are given the half-life. Now, if you do not want to find this, you can use this identity. Okay. So from this identity, half-life is given, then the decay rate will be given. So K equals 1/t natural log 1/2. Okay. So what is T? T is this number. Right. Well, you can change it. 1/2 become 2 to the -1. So you can also you can write in this form. Right? There are many ways to do. Right? You can also put 2 to the this. Right? Right? Okay. So there are many ways to express it. So the formula is, remember the formula is the initial quantity, e to the kt, right? I already know the k. I use this one so I can get e to the k. K is this number, right? K times t, t times k. So natural log of 2 to the negative 1090. Okay, so I can move t to the here. All right, finally, you can even get the e and the natural log. Okay, so this is a formula. It decays exponentially. Okay, when t equals 1590, and it'd be 2 to the -1, so you divide 100 to the 1/2. You can double check that, right? In the 1590, and that is going to be 2 to the -1, right? And that is just the 100 divided by 2, so it's 50. Okay, 50 mg. Okay, that's why it's called half-life. All right. Now the next one, the second problem is we want to find the mass after 1,000 years. 1,000 years, I think, is shorter than 1,590 years, right? So I think it's not going to be half-life. Probably, my guess is maybe 80, about 70, whatever, right? Because 1,000 is shorter. So all I have to do is once you get the formula, right? So you just estimate 2 to the 1,000 divided by this. Okay. You estimate this, okay, and using calculator, you can only after estimate it's about 65 mg. Now look at this, right? Of course, it's more than half, because otherwise it's 1,000 will be, the half-life will be smaller than 1,000. Half-life actually is 1,590 years. So that's why before you reach to that time, the quantity is still bigger than 50 mg. Okay, but in reality, is we want to also want to find the number of years, find Yeah, we want to know when will the mass be reduced to 30 mg, okay, or even 10 mg. Okay. Right? Well, just look at the above identity. We have the identity, right? We know that you write down the equation, right? E to the negative t 1590, right? So that's just the formula. What you want to do is find a time such that this is going to be 30. That's okay, just find t. So you get the equation. Yeah. You must do some exercise like that. Otherwise, you're confused about what do you want to find out. I see still 5 students out of 35. You'll be confused about this kind of problems. Okay. The very important thing is to determine the coefficients in the formula. Okay. Then once all the numbers given, is determined, then you can solve all the problems here, electric problems. All right. So you have to simplify it. It's going to be 30 over 100, and that's 3 over 10. Okay. So I'm trying not to use a calculator here. Okay. So then I put the natural log to the both sides. I get natural log of 3 over 10. Okay. Right. So the answer will be t equals negative 100, 1590, natural log of 3 over 10. Wait a minute. Am I right or not? Yes. Yes. I'm not. No. Where's the natural log of 2? Okay, let me go back, okay? I think I lost the one term here. Somewhere. No. This is a 2. Yeah, not an E. So, yeah, this is my mistake. It's 3 already. Already put a 2 here. Okay. It's not an E anymore. Yeah, it's 2. I copied it wrong. Okay. So if I put a natural log on both sides, and I get here's natural log of 2 here. Okay, this will be natural log of 2. Okay. Yeah, then you solve for t. So you get the expression, and if you don't have time, don't use a calculator, just leave it like that. This is the correct answer. Okay, and then if you use a calculator, you estimate it, it's going to be 2,762 years. That's a really long time. It's hard to imagine in 2,762 years, like, okay, what kind of world would be, okay? And the technology grows so fast, we're in a couple of years, so everybody probably uses 5G, then 6G, right? 5G, how 5G can be used. If the speed is 5G, then as long as there's equipment in some clinic, you can have a bigger surgery over there instead of going to IU hospital or some bigger hospital, because the doctor even can do the surgery at his home, connected. Okay, put the gloves on his hands and just on the computer he can cut this, cut that. Okay, and there's a machine over there just do the surgery. So it's a 5G. Okay, and I already did that successfully on the dog. I haven't tried for a human being. Okay, so it's really, yeah, when I was a graduate, it's hard to imagine right now everybody has cell phone and can do lots of things. Okay, I still remember the first day we were told how to use the email. That was let me think about. That was in 1982. Okay, that's a long time ago. I'm older. 1982 at State University, New York, Stony Brook. I was a student, and we were told that we can use an email, communicate with the professors. Okay. All right. So, but I think there was almost no hard disk memory. It's very even 1991. That was 10 years later almost. Finally, I can have my own first computer, home computer. The hard disk drive memory is 200 megabytes. Can you believe that? But I still can. I can use that to type of papers, write, submit homework, something like that. Okay. All right. So next problem, I'm going to talk about Newton's rule of cooling. Yeah, Newton's a special guy, and he paid attention to everything around him, and then he can use mathematics to derive the formula and discover the laws. Okay, and that is a person. We see everything, okay, around us. Probably we never bother to even try to figure out what's going on. Okay, so Newton find out if you put an object in a surrounding area, and if we like a TS is a TS is a temperature, for example, temperature of the surrounding. Okay, and the T means the temperature of the object. Okay, now I think very few people, even parenting kids, for example, they never even think about high school students. If they're not studying this stuff, how the temperature decrease, right? And right, they know that if you take the ice bar out of a refrigerator and put on the table, and then it's gradually, it's a meltdown. The temperature increases. But almost nobody is trying to do some experiment and analysis and can predict the temperature of the object after you move out from the refrigerator, like in 10 minutes, in 30 minutes, okay, assuming the room temperature is constant. Yeah, so you can tell where, the difference between the two kids is where this kid will eventually become scientists if he keep asking the questions and trying to do some small experiments. Okay. Okay. So Newton find out that the rate of change of the temperature, okay, so this will decreases, okay, is going to be, it's not necessarily decreasing, it's increasing sometimes. If you take the object from the refrigerator, then, it's increasing, okay, the temperature will be increasing. But if you move away, very hot object put in the room right on the table, and then it will be cooling down. So that will be decreasing. So it's really depends, but we know that it's proportional to the difference between the temperature and the room temperature. Okay. Okay. So if the difference between the two temperatures is getting smaller and smaller, then the rate of change of the temperature of the object will be getting smaller and smaller. It's a proportion to that. That's what he discovered. Okay, after do lots of experiments. Okay, and then you write down formula. So then the constant K depends on its object. Constant K depends on object. Okay, constant K depends on object. Right, so different constant, and then different object, different constant. Okay, so this is an equation. Now we cannot use our original equation to get the formula for T, right? How do you do that? Well, if we use a substitution, let Q to be T minus TS. TS is constant. the room temperature is constant. Then you will see that dq dt equals k times q. You think, wow, that's an equation we are familiar with. Okay, so therefore, you have this equation. Okay, therefore you have this formula. Then you change it back. That's a Ts minus Tm. Okay, so this is our formula. Okay, that's what you need to find out. All right, so let's do the problem. Let's work on the problem. So we know that as initial temperature and T there equals 5 degrees. And after the room temperature, Ts equals 20 degrees, okay? So after 25 minutes, when the object is put in the room, its temperature is increased, of course, increased to 10 degrees, okay? After 25 minutes, okay? Okay. The temperature of the object, okay, is increased to, okay? So that's what we observe. Then you have to do some prediction, right? So what is the temperature of this object after 15 minutes? Okay, what is when it when will the temperature be 15 degrees, for example? We have many questions to ask. So the first question is, what is temperature, okay, after 50 minutes? Okay, to solve this problem, you needed to go back to to solve this problem, you need to go back to the formula, right? So the room temperature is going to be 20, right? And the initial temperature is 5, the object, right? And the room temperature is 20, e to the k times t. So this is, so let's see how much we know, okay? We know that t of this is going to be 20 minus 15 e to the kt, okay? So we are given some information. Yeah, after 25 minutes, the temperature is increased to 10. So 25. Okay, in this case, we can determine the constant k. So that will be 10. Okay, let's go back. Yeah, we don't need to move 20 to the right-hand side, probably. So we move back 20 to the left, is negative 10 equals negative 15 e to the 25k. So e to the 25k is going to be 10 over 15. It's going to be 2 over 3. Okay. So k is negative because it's the temperature. Yeah. So k is negative number. Okay. So k is negative number. So 25k equals natural log of 2 over 3. So you can write down the k equals 1 over 25. Let's put it this way first. Okay. So we get a constant. Okay. So when t equals 50, right? 50 minutes, after 50 minutes. Once you get a k, you can solve the problem. Then t over 50 equals 20 minus, that's right, 15 e to the k times 50. Okay? It's not too bad. Okay, so it's going to be 20 minus 15 e to the 50 times k. 50 times k is 50 divided 25 is 2. Okay? And then you write as like this, right? So E natural log will be cancelled out. And there will be 2 over 3 squared. Okay. 2 over 3 squared is going to be 9 over, yeah, let's find the integer, okay? I think we can even find the integers, 4 over 9. So this cancels out, 3, here's a 5, right? Right, so 4 times 5 is 20, so it's actually 20 times 2 over 3. So it's actually is going to be 40 over 3, okay? Your estimate is 13.3 degrees, okay? So 15 minutes later, the temperature increased to 13.3 degrees, right? And 25 minutes, after 25 minutes, the temperature is 10 degrees, you see, right? So here's a picture, right? 5 degrees, and T equals 25, so it's 10 degrees, and then T equals 50, it's 13.3 degrees, okay? It's not like increasing so fast, it's getting slowed down. Yeah, all right. Our next question is, when will its temperature be 15 degrees? Be 15 degrees. Okay, so 15 degrees. I think should be somewhere here, right? 15 degrees, right? No, 15 degrees not. Somewhere here. So it's much longer. Okay, so why we need a picture here? Because somewhere here, 15 degrees, then T must be larger than 50 minutes. Okay, if you get numbers smaller than that, it's wrong, right? So it should make sense, you know. Yeah. Okay. So again, let's write down the formula. So this is a 5 minus 20 e to the k times t. Okay. What is k? Well, I forgot the k, right? K. Let's go back to k. K is going to be 1 over 25 natural log 2 over 3. K is going to be 1 over 25 natural log 2 over 3. Okay. So we're just trying to find t so that this should be equal to 15. Okay. When the temperature is 15, what is time t? So let's write down this, okay? So 15 minus 20 equals 5 minus 20 e to the kt. So it's negative 5 equals negative 15 e to the kt. Not too bad, right? Yeah, you simplify it. And the e to the kt equals 5 over 15. It's 1 over 3. Well, good. So then you haven't put the natural log. Kt equals natural log 1/3. Okay. And the t, what is t, right? What is k, right? Let's write down the k. K is going to be okay. So let's compare both sides, right? And this is a k, and that is a t, right? So both sides I'm going to multiply 25. Right, so t is going to be 25 natural log 1 over 3 over natural log 2 over 3. That's it. You have to estimate. Okay, you have to estimate. This is a number larger than 25. Right. It's numerator and denominator both are positive, both as a negative, right? So you can change it to 25 natural log of 3 over natural log of 3 over 2. Now, natural log of 3 is greater than natural log of 3 over 2 is greater than 0. So clearly this is going greater than 25 minutes. Okay, but even 50 minutes, I'm pretty sure it's greater than 2. Okay, it is greater than 2. Because I already predict it's greater than 50, right? 50. So let's see why this is greater than 2. Yeah. Yeah, let's take a look at this. I don't have a calculator. I don't want to use a calculator. You should be familiar with oops. Yeah. All right, so natural log of 3, y is greater than natural log of 3 over 2. Well, we put the question mark here. Let's calculate this side. Natural log of 3 over 2 squared. So is 3 greater than 3 over 2 squared? Because 3 over 2 squared is 9 over 4. Yes, that's true. Okay, so that's why 3 is greater than 9 over 4. That's why natural log of 3 is greater than natural log of 3 over 2 squared. Okay, that's why it's greater than 25 times 250. Okay, my answer should be correct. Okay.